All right, you have some experience now with solving exponential and logarithmic equations, but the ones you've worked on were very specific types. We're going to expand your repertoire now, so you can do some other types that are exponential and logarithmic as well. In your exponential equations, sometimes you can't rewrite them so that you have the same base on the two sides or the same exponent on the two sides. And when that happens, you have a technique where you can take the logarithm of both sides of the equation. There's a lot you can do to equations because of that equal sign. As long as you keep it balanced and do the same thing on the left as you do on the right of the equal sign, there's a lot of operations you're allowed to do. And in this case, taking the logarithm is included. So you can take the logarithm of each side, then use your properties of logs and your basic rules of algebra and solve. But then always check your solution because it's possible you can get solutions that aren't going to work in the original equation. So always go back, make sure it's going to work. And a little hint too, if you see the base is e, use natural logs. If the base is e, use natural logs. If the base is 10, use common logs. Makes things easier. And by the way, this method you're going to do also will work on type 1 exponential equations, but it's just so far those equations we've been able to rewrite them so that the bases are the same or the exponents are the same. But if you don't want to go through that process on those problems, you can also take the log of both sides and do them. Okay, so let's look at a couple of examples of just how to take the log of both sides and solve an equation. All right, starting out with, let's say you have the equation 5 to the x equals 13. Well, you can't rewrite this so that you have the same base. You can't easily do that because a base of 5 and a base of 13, you've got two prime numbers there. You can't really do much there with factoring or multiplying or anything like that. And one of them has the exponent of x, the other doesn't. The other has an exponent of 1. So that's kind of complicated. So what we're going to do is we're going to take the log of both sides. Since it's numbers, I'll just take the regular log. I mean, if you really want to take the natural log, you can. Either way, doesn't matter. All right, properties of logs. Let's see. X, since this is an exponent in the argument, you can put it out front and multiply it. You have x times log 5 equals log 13. And then you can go ahead and use some algebra. Remember, log 5 is a number. Log 13 is a number. If you don't believe me, just put it in your calculator. Find the log of 5, you'll get a decimal. Find the log of 13, you'll get a decimal. So you can divide both sides of the equation by log 5. That's perfectly acceptable to do. And then you'll have x equals log of 13 over log of 5. And that is your exact solution. Now, if you want a decimal approximation, that was loud, I'm sorry. Turn that down. Decimal approximation in your calculator, log without a base is log base 10. So log 13, make sure you close the parentheses, divided by log 5. Again, close the parentheses. So there's your decimal approximation, around 1.594. And if you take 5 and raise it to that power, 1.593692641, and you don't have the full decimal, so you're not going to get it like exact, but you can tell what it's supposed to be. The answer is supposed to be 13, and that's exactly what we expected because 5 to the x equals 13 was the original equation. Okay, so you could say it's exactly log 13 over log 5, or you could say it's approximately 1.594. Okay, let's do another one of those. Let's say you have something like 3 to the x minus 4 equals 7 to the 2x plus 5. All right, another example where I just can't rewrite these to have the same base and the exponents either. So it's going to be easier just to take the log of both sides. And since the arguments have exponents, we could put those exponents out front and multiply. So we have x minus 4 times log of 3 equals 2x plus 5 times log of 7. Interesting. Now, log 3 and log 7, again, are just numbers. So you have x times log 3 minus 4 times log 3 equals 2x times log 7 plus 5 times log 7. Let's see. Subtract the x's. Decide which I want to do. I think I'm going to subtract 2x log 7 from both sides. And I'm going to add 4 log 3 to both sides. All right. I can factor out an x from here. I have log 3 minus 2 log 7. Then I can divide both sides by log 3 minus 2 log 7. And there you go. That's the exact solution right there. If you want a decimal approximation, just punch that in your calculator and see what you get. But that exact solution, if plugged in for x up into this original equation, will work. And that's what you want to do if you want to check it. It's plug it back in up there. All right, we'll do one more of those. This one has an e, so that way we can have a little bit of experience using natural log. E to the 0.5x equals 3 to the 1 minus 2x. So again, the exponents, I can't get them the same, or the bases. Now, since there's an e, it's advisable to go ahead and use natural log of both sides. And if you're using natural log on the left, you also need to use natural log on the right, because you gotta keep it balanced. Do the same thing to the left as you do to the right. But the convenient thing, if you think about your properties of logs, taking log base e of e to the 0.5x is just going to leave you with 0.5x. Go back to your properties of logs and you'll see that. And then on the right, that exponent of 1 minus 2x can go in front of natural log 3. So you got 0.5x equals natural log of 3 minus 2x times natural log of 3. Let's see, add 2x natural log of 3 to both sides. That equals natural log 3. Factor out x. You'll have x times 0.5 plus 2 natural log 3. Divide both sides by 0.5 plus 2 natural log 3. And you'll get natural log of 3 divided by 0.5 plus 2 natural log 3. And there's your exact solution right there. So that expression, when plugged in for x up here in the original equation, will work. Okay, so there's some examples of how to tackle some exponential equations where you can't get the bases the same or can't get the exponents the same. You can take logarithms of both sides, either log or natural log, just depending on which one's more convenient for you. You can take any log you want. You can take log base 3 if you want. It doesn't matter, but since your calculators deal with common logs and natural logs, it's good to stick with those when you're allowed to. All right, and then more on log equations. If you have a log equation that has more than one log, you might have to apply the properties of logs to get the equation into a simpler form. You know, kind of bring it down into one logarithm on one side instead of multiple logarithms. And if you can get the log equation into the form of a log equals a log, as long as they're the same base, then you can set the arguments equal. And then make sure to check your solution, make sure it's going to work. Because here in these log equations, it's possible to have solutions that aren't going to work, that are extraneous. So you got to go back and check, make sure they're in the domain and will work. And if you can get the equation into the form log equals some number, then you can just rewrite an exponential form and solve the exponential equation instead. Okay, for example, let's say you have natural log of 2x equals 5. Remember that natural log is the same thing as log base e. Well, you can rewrite, since it's a log equals a number here, you can rewrite this in exponential form and say e to the 5 equals 2x. So x is equal to e to the 5 over 2. And that would be your exact solution. Or you can pull up your calculator. E to the 5 divided by 2, let's do it. E to the x, so second ln will give me e to the x, e to the 5, close parentheses, is that, and then divided by 2 is that. So I get approximately 74.207. And if you put that back into your calculator, or into your original equation, sorry, you got natural log of 2 times e to the 5th over 2 equals 5. So you've got natural log of e to the 5th equals 5. Well, properties of logs, the natural log of e raised to a power is just going to equal the power. So it works out. There you go. So that answer is correct. Okay, next one. Let's say we have natural log of 4x minus 2 minus natural log of 4 equals negative natural log of x minus 2. A lot of natural logs going on in that problem. So one of the first things you want to do is see if you can apply properties of logs to try to condense things down a little bit and not have so many logs all over the place. You're not a lumberjack, right? All right, so on the left side, I have a natural log minus a natural log. So I can apply my properties of logs, and I can rewrite this as the natural log of a quotient. I could put natural log of 4x minus 2 over 4. And then on the right side, negative out front is the same thing as saying negative 1 times natural log of x minus 2. So I can rewrite that as natural log of x minus 2 raised to the negative 1 power. So remember, number times a log, that number could also be the exponent in the argument of the log, on the argument of the logarithm. So now both sides have natural logs. So if a log equals a log, they have the same base, then their arguments can be set equal to each other. Then you can go through and try to solve for x with that. X minus 2 to the negative 1 is 1 over x minus 2, so that's why I wrote it like that right down here. Let's see. Cross multiply, you basically have a proportion here. So cross multiply. Looks like we're going to end up with a quadratic equation. Yay! Alright, so we got 4x squared minus 10x equals 0. Go ahead and factor. We got x equals 0. We got x equals 5 halves. So I have two possible solutions here. We do need to go back and check. We need to make sure these solutions are going to be included in the domain. Because remember, like when you're taking the log of something, the argument has to be positive. So let's go back and make sure of that. If you do a natural log of 4x minus 2, and you plug in 0 there for the x equals 0, you're going to get natural log of negative 2. Can't have that. So 0 is out. What about 5 halves? I have natural log of 10 minus 2 or 8. That's okay. So that minus natural log of 4. So that's natural log of 8 over 4 or natural log of 2. All right, and the other side, negative natural log of 5 halves minus 2. So negative natural log of 1/2. So natural log of 1/2 to the negative 1. So natural log of 2. So the 5 halves works out. So the 5 halves we can keep. So we had a quadratic equation to solve, but we ended up with an extraneous solution. But that's all right. Toss it out and keep the one that was okay, that worked. 5 halves not only fit in the domain, but also make both sides of the equation true. So it is very important on these logarithm equations to go back and check your answers. All right, let's tackle one more of these together. One more log equation, and this should be a good representation of the problems you're responsible for. Let's say we got log x plus log of 3x minus 13, and that has to equal 1. All right, so not quite as many logs going on in this problem, but still you see logs in two places. And I don't want to subtract log of 3x minus 13 from both sides because of this 1 over here. I would still be stuck with like logs in different places, but the 1 wouldn't have a log in its terms. So it's better just to go ahead and apply our rules of logs, our properties of logs. We have log plus a log, which means we can multiply the arguments together and write this as one logarithm. So we have the log of 3x squared minus 13x. Now that it's down to a single log, we can use our exponential form. It's log base 10, so 10 to the first equals 3x squared minus 13x. So 3x squared minus 13x, let's subtract that 10, that's to equal 0. So another lovely quadratic. Let's see here. I'm going to try factoring it. If you'd rather use quadratic formula, you're more than welcome. that work? 2, 5 minus plus. Minus 15 plus 2 will give me minus 13, and plus 2 times minus 5 will give me minus 10. So there we go. 3x plus 2 is 0, and x is negative 2/3. X minus 5 is 0, and x is 5. Alright, I can already tell that negative 2/3 is out. Because as soon as I try to plug in negative 2/3 for x up here, can't have it. So negative 2/3 is out already. So let me plug in 5, see what happens with that. So I've got log of 5 plus log of 2 equals 1. Or log of 5 times 2 equals 1. Well, log base 10 of 10 is 1. So that one checks out. So 5 is the only one that's going to be a solution. So x equals 5. All right, well, there you go. There's some more exposure to solving exponential equations and logarithmic equations. In this lesson, we're just going to worry about the equations and not the inequalities. And now you've seen a little bit of all kinds of scenarios. So practice, practice, do all your homework. And next time you tune in for 5.6, we're going to be looking at some applications. We're going to be looking at some word problems that involve exponential and logarithmic functions. So using all the stuff that you already have learned in this chapter. Well, thank you for joining us.